Okay, physics. Let's talk about springs. So springs can store energy the same way that gravitational field can store energy, and it's kind of a funky thing to think about, but it kind of should make sense to you. So we can think about a spring. In this case, my spring is oscillating between storing gravitational potential energy and storing the energy someplace in that twisting metal. So it's a torsional thing, right? So if you twist something, it has a tendency to want to untwist. And so that's a way to store energy. So it's a mechanical energy. We're taking those atoms and we're getting those atoms to be a little bit uncomfortable next to each other. And those atoms want to return to a more comfortable state. So it's a way of putting things into a slightly higher energy state. Curious thing about springs. So you may recall that springs are one of the few examples that we have where we have a non-constant force. So let me talk you through some of this. So we'll come up with an equation. So you may recall a Hooke's law, which said that if I plot force versus, trying to get this to focus. Hooke's law, if I plot force versus stretch for a spring, that I will find there's a linear relation from this. So the force, which is going in the opposite direction, so we give it, has this linear relationship to the displacement. So the more you push on a spring, the more it pushes back. So there's another way to it. So this is right. This is looking at the slope of the line, right? So the slope of the line tells me something. If I look at the same graph, though, and I think about the slope is going to tell me something about the spring. In this case, the spring constant, and the relationship between force and displacement. But I want to think about what the area under the curve tells me. So what's the area under the curve tell me? So for this graph, force times distance. So hopefully you might recognize that as work or energy. So I can think about what energy I could put into a spring by coming up with an equation that represents this area essentially of this triangle, right? So what's the area of my triangle? So it's going to be my 1/2 force times distance squared, right? So force times. Let me try that again. So here's my force and my displacement, and I'm looking at the area under the curve. Right? So I come up with Hooke's law, which says force is equal to negative k times x. Remember, force times distance, and that's going to be work, which is a function of energy. Right? So I can think about the amount of energy stored in a spring as being a function of what's the force that I applied over that distance that I stretched or compressed the spring. Key thing here, though, is that it's a variable force, but it's linearly variable. So let's say force times distance. Well, this is going to be this area under this curve, right? So this is going to be my work is going to be either my average force or it's going to be 1/2 my maximum force times my distance. What's my maximum force? Well, it's going to be the force at that distance. So I can plug this in. So my work is going to be 1/2 k times x or 1/2 kx squared. So this is an equation for the magnitude of energy that can be stored inside a spring. So notice I dropped this negative sign because force, that just is indicating the directional difference between my displacement and my force. And here I'm talking about the work that's going into compressing an energy. So I'm adding energy in, so I need this to be positive. Anyway, so this is our equation for energy that's stored in a spring. And notice what it is. So now we have another way of storing energy. Remember, I can have kinetic energy. I can have energy that's stored in the gravitational field, so a gravitational potential energy. And we had two flavors for this, so when you're close to the surface of the Earth and when you're far away. And I can also now store energy in a spring, sometimes we call it elastic, although I don't like to use EL because we'll have electrical potential energy later. And all of these are going to be components of what we call mechanical energy. So these are useful energy, things that we can transfer from one spot to another spot. Total energy, right, is going to include sound and friction and heat and deformation and things that are really tricky to keep track of. So mechanical energy is useful energy, and it includes spring energy. Spring energy we can calculate with 1/2 kx squared. So what does this look like? Well, if I have a spring, say I'm going to roll a ball down a hill, and it's going to hit, this is my spring, right here's my ball going. If I give some numbers to this, right, I can figure out, so what's going to happen, right? I'm going to have gravitational potential energy. It's going to get converted into kinetic energy, and then when that spring comes to rest, that'll get converted into spring energy. Right? So I give it some height, h. I'll say the initial velocity is 0. It's going to start from rest. It's going to have a height. I don't know. We can give it some numbers. Call it 1 meter. I'll need some spring constant. Say this is 50 newtons per meter. And I'll give it some mass to my ball. So my mass of my ball is going to be, I don't know, 0.5 kilograms. I want to know, so how far is this going to compress? So how far will the spring compress? Again, like all my energy problems, I want to start out saying the energy that I start with is going to be the energy that I end with, all right? So I'm assuming this is losing no energy to friction or other things. This is maintaining mechanical energy. This is my way of stating that assumption. So I'm going to start with gravitational potential energy, and I'm going to end with potential spring energy. I can write an equation, mgh, and this is going to be equal to 1/2 kx squared. And I can rearrange this so x squared is going to be 2 mg 2 mgh over k, and I'll square root both sides. So x is going to be root 2 mgh over k. And I can plug in some numbers to get to an answer, but I don't feel like it right now, so I'll leave you to do the calculator work. Anyway, the idea is that you should be able to use spring energy as just another storage place for energy, and the things to go with that. So a couple things to be careful of, right? So I want to be careful about this. So if I have a spring that's oscillating, right? It's going back and forth, right? So if I have the spring by itself, it's going to have some length here. When I put my mass on there, it's going to stretch it down, right? So that how far it stretches is the distance that we use in our spring calculations, right? It's not the total distance, it's the distance that it stretches. So I have to be careful about how I measure this, is that I want to see how the spring stretches, not the total distance. It's a common mistake in these questions. Anyway, hope that's helpful, and talk to you soon. Bye.